sulfur atoms we have seen. Out of these 4 sulfur atoms, 2 zeros, 2 minus 1s you got. Therefore, in that net 4 atoms, total minus 2. So, it looks like minus 1 by 2, but it can't be a fraction, but it is appearing like that when you take certain averages. But actual state when we need, by structure only, one should find what is the exact oxidation state. And like this, when oxidation state of elements could be understood, we can now extend our discussion to decide in a reaction which reacted as an oxidizing agent, which reacted as a reducing agent, therefore, what is this N factor, what is the other one's N factor, etc. But before going to that work, we need one more thing to consider. Because actual oxidation state meaning we understood by looking at the structures and bond combinations, etc. But in practice, for every compound, we cannot go on using these structures and getting the actual oxidation states. Therefore, we try to have a short list of certain oxidation states, so that other ones at once we can understand, at once we can find out from its reaction. Those are depending on the nature of the element. Some elements we notice, we find having certain oxidation states always. Therefore, we can use them in finding others oxidation states. For example, if you look at the sulfur in that earlier example, same sulfur atom in one state, one place it has 0 state, other place it has -1 state. Like that, variable oxidation states are possible. In that case, it is difficult to predict in one particular example what is its state. But there are some elements which do not have that much variation in their behavior. For example, alkali metals, hydrogen, oxygen, alkaline earth metal, some elements they have definite oxidation, certain oxidation states. So what we try to do is we remember those oxidation states, and using these oxidation states we try to find other uncertain or less definite oxidation states from these calculations. For this, we can have one workout like this. Standard oxidation states. Here, this short list is useful. All alkali metals, like sodium, potassium, etc. in compounds have always same oxidation number +1. And alkali metal, sodium, potassium, etc. in whichever compound found, its oxidation number is same. Next, alkaline earth metals, these also, like calcium, magnesium, etc. these also have definite oxidation states in compounds. In compounds, they have same oxidation state always, that is +2. We don't have any doubt about this. Unlike sulfur, we have seen sulfur having different states in different structures, but these are not. Similarly, some like zinc metal, its oxidation number always +2 in every compound. And silver always has same oxidation state in its compound, that is +1. Similarly, aluminium also has same oxidation state always. In all its compounds, it has a definite oxidation state +3. In halogens, this fluorine has a definite oxidation state, that is -1 in compounds. So these are examples with definite oxidation state. Every alkali metal in every one compound +1. Every alkaline earth metal in every one compound +2. And a zinc in every compound, zinc sulfate, zinc phosphate, whatever you take, its oxidation number +2. Silver in all compounds same +1, aluminum in every compound +3, F fluorine in all compounds -1. So this will help to understand other one's oxidation state. Suppose an unknown substance, some X is with F forming a compound. We can tell because we know that fluorine has always same oxidation number -1. Here also 2 fluorines must be in 2 -1 states. So as a net we can tell X value here or X state here should be +2. Because as a compound, every compound is neutral. When there are 2 minus charges coming from 2 F atoms, it should be in +2 state only. Like that, oxidation state of unknown element we try to predict when we know at least one or the others. Similarly, in other cases also, aluminium etc. can be taken with their regular standard definite oxidation states. And after this, we have some more examples like this, but not so much rigid. In these, we always find same state, but similarly, others, oxygen, hydrogen also can be expected to have certain definite oxidation states. Those also we can list. So after this, the other things we need, we can remember as the standard states are these. Oxygen. Oxygen usually -2. Like that, hydrogen, it is usually +1. If you observe, in the previous 6 cases I told, they have certain definite oxidation states. But when I come to these two, I am saying usually -2, usually +1, because these have some exceptions. That's why I could not say that always -2 like in other cases, but helpful, because mostly we find, except in few cases, except in H2O2 like peroxides and fluorine compounds, etc. Otherwise, it is always -2. Similarly, hydrogen in all compounds +1, except in metal hydrides. Except in metal hydrides, usually it is +1 state only. Therefore, we can consider these also like the previous set of examples. We can take these also almost with certain definite oxidation states only. In this way, when we have this definite oxidation state, how can we use them to find the oxidation state of any other element in a compound? This we see with some examples now. After having this short list of certain oxidation states, our interest is to find oxidation states of other elements which are not always having certain states. For example, if I find an example like potassium permanganate, you can easily observe there are 3 elements: potassium, manganese, oxygen. Out of these, if you recollect, just now we had a short list in which we found certain definite oxidation states. Among them, potassium we found, it is an alkali metal, in all compounds same state. Oxygen also we found almost same, -2 oxidation state we find for oxygen. So now doubt is with Mn, because that can have number of states. Because we know that those elements like oxygen, potassium etc. have definite oxidation states, and we also know that a compound has net charge equal to 0. With this information, we try to find out what is the oxidation state of that Mn. Simply like this. As we know, potassium oxidation state 1, 1 plus 1. I mean 1 potassium atom, each one plus 1 state. Plus 1 manganese atom, I don't know its state, say X. Plus, there are 4 oxygens, but each one we believe generally it is always -2 state. Summing all these, net charge, that should be 0. Therefore, you can tell X equal to plus 7. In this way, one can understand manganese in this compound, potassium permanganate compound, has oxidation state equal to plus 7. And example, other example, say potassium permanganate or sodium permanganate or sodium manganate, number of compounds we can take. Look at this. It is manganese